Hello and welcome everybody to the power system protective settings in the DIgSILENT environment. Today I would like to talk about distance protection settings using ACL 421 relay model, which combines high speed distance and directional protection. I am going to divide this video into 3 parts. In the first part, I will give a brief information about distance protection. In the second part, I will talk about how to setting the distance relay protection in the DIgSILENT software environment. And in the third part, I will talk about how to create RX plot and time distance diagram, and will verify the different fault location and tripping time for different protection zone. Okay, let us start and learn them step by step. We have discussed about overcurrent relays, so why we should go for distance protection relays instead of overcurrent protection relays. For short transmission lines, overcurrent relay is a good enough for protection when directly connected to generator. But in complex power system, all transmission lines not necessary to be connected directly to generators. So in this case, overcurrent protection relays cannot provide proper protection. Consider this simple line diagram circuit, which source is directly connected to the bus. And here, this is a circuit breaker used for opening the switch. And this is a CT or current transformers to provide current to overcurrent relay. Now suppose that there is a fault occurring anywhere on the line, and the current measured by the relay is the source voltage over line impedance from the fault. So there is no problem in the operation of the relay. If there is impedance right next to the source, then at different location of the fault, the current measured by the relay will be different. Due to the voltage drop in the source impedance, and the source impedance is the Thevenin equivalent resistance present in the left-hand side of the bus. In such a case, the current measured due to a fault here will be different, while source impedance varies. Therefore, the overcurrent will not be able to discriminate the location of the fault exactly. If we consider different types of faults, such as phase-to-ground fault, phase-to-phase fault, double phase-to-ground fault, as you see, the expression provided here for phase-to-ground fault, phase-to-phase fault, and double phase-to-ground fault, the current due to a fault at the same location is different for different types of faults. Therefore, the relay cannot operate properly. If we consider this diagram, we see that the fault current is decreasing as we move further from the source, and we already discussed about. But the location of fault is different for these 3 types of faults, because at the same location the current due to a fault were not the same. As you can see here, the fault current for 3-phase fault is greater than line-to-line ground fault and line-to-ground fault. So we can say that fault current depends on types of faults. Therefore, the length of line which is protected depends on the types of faults. Because the fault current depends on the source impedance, fault types, and voltage source, therefore it is not efficient to make use of overcurrent relays, and can be used only for simple cases where a radial line is directly connected to a generator. But in case of a complex system, to protect it, we need to use another type of relay, which is known as distance protection relay. Distance protection relay is actually independent of the characteristics of generators and the fault types. So let's go to the typical arrangement of distance protection. For this type of relays, we have both current and voltage transformer, and it obtains signal not only from the current flowing in the line, but also obtain signal from a potential transformer. There is the relay setting Z impedance, known as replica impedance, which is an equivalent impedance of the line, and multiplying by CT and PT ratios. Then an equivalent impedance which is connected inside the relay will be obtained. So the value of the replica impedance, currents and voltage are justified to provide the exact location of the fault point. Suppose there is a fault on the line, then the relay will find the ratio of voltage and current. So it will measure the impedance between the bus and the fault line, which is the ratio of this voltage by current passing through this line. And the measured impedance of the relay will be independent of the source impedance, and the varying of source impedance will not affect on value of impedance measured by the relay. Note that the impedance measured by the distance relay is different for line-to-line fault, line-to-ground fault, and double line-to-ground fault. Therefore, the distance relays are made separately for each different types of faults. So, for an actual network system, for one relay, there are 6 relays. 3 relays are for phase fault detection, and 3 of them for ground fault detection. And we will see that in the relay settings in the second part of this video. For the backup purposes, we need to emphasize the concept of timing of zone protection. The relay which is located here can protect zone 1 up to 80 to 90% of the line section. And there is not any intentional delay, so it is instantaneous protection, and it responds immediately for the events. As you notice, there is also a little gap here which is from 10 to 20%, so that any fault occurring near to this bus close to this circuit breaker must sensed by this relay, and it shouldn't wrongly measured by this relay. But if this relay does not operate to clear the fault here, then there is a timer inside the relay, and that will change the value of ZR so that will enable the relay at this location to measure fault up to zone 2. And zone 2 provide 10 to 20% protection of the remaining primary line and up to 50% of the next line. So the fault anywhere up to the middle of this line will be detected by the same relay, but after a time delay. After some more time delay, ZR will increase more, and our relay will cover the third zone up to 10% to 20% of the third line. For example, if this relay does not protect, then the backup will operate, and this relay will trip after a further time delay. So it provides the full backup to adjacent line section. So in this zone, it provides the protection of line 1 plus line 2 and plus 20% of the third line. As a result, if these relays do not operate, then after time delay, this relay will trip if the fault occurring anywhere on this line from this point up to 20% of the third line. So this is the backup protection. Okay, let's turn to the second step, which is about the setting of distance protection using SEL421 relay model. This is a single line diagram of 6-pass network system with 2 external grids feeding power from both sides. There is 4 transmission lines with 3 general loads and a transformer. So let us implement our distance relay protection on the first line, here next to the first bus bar. So right click here, from New Device, select Relay Model. Then from Relay Type, select Project Type. I have already imported the relay model that I am going to use. If you don't know how to import that, you should watch my previous video which is about overcurrent relay protection. Select SEL421 1 ampere and click OK. Name it SEL421 1 ampere. Then create CT, whether you can create a new project type or you can get it from the DIgSILENT library. In the relays, click on CT and select CT 120, 1000 or 1 ampere. Click OK. Primary tab is 120 and secondary tab is 1 ampere. Click OK. Then create VT, select project type from the library. Click on VT. Primary tab is 20,000 volt line to line and secondary tab is 100 volt line to line. Click OK. Then go to the polarizing Z1 element. The value of constant K0 and angle will be updated automatically by clicking on Assume K0. K0 is earth factor magnitude and this is the earth factor angle of our transmission line. Do the same thing for polarizing Z. We are not considering out of this step because there is zone 5, zone 6 that we will not be used in this project. So make it out of service. Then double click on 50 pp starting. Here you will notice earth fault detection and overcurrent element. To pick up all faults at the end of the setting zones, we need to set them sensitively. So we need to calculate the 3-phase and earth fault current at the end of zone 3 for relay on line 1. The end of our zone 3 is here. Calculate 3-phase short circuit, and short circuit current is 4.44 kA. Keep it in mind and calculate for single phase to ground, that is 2.426 kA. Open again your relay setting. Enter the 3-phase fault current for the earth current and single to ground fault current for overcurrent element. Click OK. In the next step, set your zone protection for phase element. Double click on first zone Z1 MP, and here you will see the line impedance, also the angle. With this default setting, the branch angle reaches about 10.32% of the line impedance. So we need to set the replica impedance to change the branch angle reach to 80% of the line impedance. Suppose the relay angle is 70 degree. To calculate the replica impedance, multiply this line impedance by 80%, then divide that to cos 78.96 minus 70. That will be 15.49. Now you can see that the branch angle reach set to 80%. The library direction can be forward, reverse. If you click here from directional, you will see all the options: forward, reverse, external, and reverse external. From here you can change the range of replica impedance and the increment step. Also you can change the range and the step change of your relay angle. So in my case, I don't need to change them and I will put them as a default setting. Click OK. For zone 2, make tripping direction forward as zone 1. Relay angle is 70 degree, and for calculation of the replica impedance, do the same procedures as we did for the first zone. But in this zone, the reach at branch should cover 150% of the line impedance. It means line 1 plus 50% of the second line. So multiply this line impedance by 150% and divide to cos 78.96 minus 70. That is 29.0.4. For zone 3, tripping direction is forward. Relay angle is 70. And for this zone, the reach at branch angle, assume it to 230 or 250% of the line impedance. If calculated, you will get 48.42 secondary ohms. Click OK. We are not considering zone 4 and zone 5. Make them out of service. So follow the same procedures for the ground elements as we did for the first element. In the first part of this video, we discussed that the impedance measured by the distance relay is different for line-to-line fault and line-to-ground fault. So in case of the ground fault, it will take the settings of the ground element. Tripping direction is forward, replica impedance is 15.49 and relay angle is 70, and here you will notice that it covers 80% of our line impedance. Click OK. For zone 2, tripping direction is forward, replica impedance is 29.1 and relay angle is 70 and will cover 150% of our line. For zone 3, tripping direction is forward, replica impedance is 48.42, relay angle is 70 and will cover 250% of our line. For the calculation of replica impedance, you can follow the same procedures as we did for the phase element and not considering zone 4 and 5. This QP and QG settings are for quadrilateral shape of phase elements and ground elements of RX plot. So no need to consider here. But if you consider, you can do the setting from here. For example, you can change the type, the directional, the range of Z reach, R reach, and the relay angle. But I don't consider them and I will make them out of service. Z1 PD. It is a phase element distance for delay. As we discussed that in zone 1 there is no time delay and it operates instantaneously. So assume time setting as 0. In zone 2, as the full time setting is 20 cycles, which is 0.4 seconds. From here you can show it in second. Let's change it to 0.3 second and this one 0.5 second. Similarly, do the same thing for ground elements. 0 time delay for zone 1, 0.3 second or 15 cycle time delay for zone 2, and 0.5 second or 25 cycles for zone 3. And make these elements out of service. And for the logic elements, no need to bring any change. Leave them as it is default. So we finished the relay settings. Now we can go to the last part of our videos. In the last part of our video, I am going to create an RX plot and time distance diagram and will verify the zones of protection. In order to create an RX plot, so we need to create a path. So hold down the Ctrl K and select bus bar 1, line 1, bus bar 2, line 2, bus bar 3, line 3, and bus bar 4. It means this is the first zone, this is the second, and this is the third zone. Then right click on the selection part. From path, create a new path and name it as path 01. Click OK. And that will save in the network data. As you can see here, if you double click it, you will see the bus bars and branches that you selected them as a path. By clicking on toggle, you can change the direction. If you right click on path, from show you can create RX plot. And you can also do that from single line diagram. Right click anywhere on the path, then from path, click on RX plot. That is how our RX plot looks like. This is zone 1, zone 2, and zone 3. Also, this is the transmission lines. As you can see, this segment is line 01, this segment is line 02, and this segment is line 03. If you double click on each of these segment lines, you will enter to its characteristics. It is also possible to edit the RX plot. From here, you can change the relay color, style, and weight. Also from here, you can change the axis scales. From the option, you can change the unit to primary ohm, secondary ohm, or percentage of line. You can also select different relay units and zones from here. This setting is for short circuit elements, and from here you can also represent the out of service elements. If you change the color, you will see all of them. So there are many options to change the style of your RX plot and bring any other changes as you wish. Okay, now let us apply the fault to verify the tripping time of distance relay protection. Let us calculate the short circuit of zone 3 line. Fault type is 3-phase on 50% of line. Now you can notice that the fault is out of your zone 3, so none of zones operating. Let us decrease the fault percentage of line 3 to 10%. Now you can see that the fault is on our third zone and the tripping time is 0.515 seconds. Apply it to second line. Now the fault is in the second zone and the tripping time is not appeared. Let us do that. Now you can also see the tripping time for zone 3. Apply it to the first zone. Now the fault is in zone 1 and tripping time for zone 1 is 0.015 seconds. For zone 2 it is 0.415 seconds and 0.515 seconds for the third zone. So you can also apply single phase to ground fault. Okay, let us verify the difference between line to line fault and line to ground fault. So let us apply 3-phase and single line to ground fault on 30% of line 3 and see if there is any change between them. Firstly, make a calculation for 3-phase short circuit on 30%. You can see that the fault is out of zone 3 and the relay is not tripping. If we calculate for single phase to ground on the same line for the same percentage of line, you will see that the fault is on zone 3 and the tripping time is 0.515 seconds for zone 3 MG ground element. So as we discussed already, that the impedance measured by the distance relay is different for line to line fault and line to ground fault. Therefore, distance relays are made separately for them. So finally, let us create time distance diagram. Right click anywhere on the path. From show, click on time distance diagram. This is the time distance diagram. That zone 1 cover 80% of line 1 and zone 2 cover 50% of line 2 and zone 3 covers 50% of line 3. In y-axis, you will also see the delay time, which is 0 for zone 1, which we defined that as intention delay. For zone 2, we applied 0.3 second, and for zone 3, 0.5 second, as you can see here, but you cannot see the exact time value. That is because of a small time delay due to the contact relays that would be added to the time delay. That is all for this tutorial. I hope it was helpful and easy to follow. If you found this video useful, then please like the video, also subscribe. Thank you for watching the video and see you in the next video.